Hello everyone. Today we're going to talk about this 5.4 applications of the vectors in the geometry. Okay, so in the previous sections we already encountered some questions involve the close link between the vectors and the geometric features, right? To take this further, let's consider more such problems where vectors can be applied to resolve the problems in geometry. So in this lesson, we're going to learn how to use the vectors to resolve some problems in geometry. Okay, so this is the K, right? So for this lesson, we will learn. In this lesson, we will learn. So how to use vectors to resolve problems in the geometry, right? So this is the things we're going to learn today. Okay, let's continue. Okay, just look at the diagram here. So basically, we have a diagram. It's a A, B, C, D. Okay, so basically this is the typical. Quadrilaters. It's a typical quadrilateral. Okay, so and then we also have some direction of we can see that this is the vector AB and this is the vector DC, right? Okay, so let's look at the first one. Okay, so if in this diagram, so if AB equals to the DC, okay, so which means they're equal to each other, and then we also, so if we say these two vectors, so these two vectors are equal to each other, then from there we will know that. Okay, then immediately we will know that. Okay, so AB is these two lines is parallel to each other, and AB, the magnitude also equals to each other, right? So that is because they are the equal vectors, right? So from here we know that they are parallel to each other. They are also direction same direction, parallel to each other. They also have the same magnitude, right? Okay, so this is the thing. So from here we also can see that because these two vectors are equal to each other, they are parallel to each other, they have the same magnitude. Okay, so from here we can see that. Okay, this ABCD, this quadrilaters ABCD is also a parallelogram, right? So from here, from these two, because these two vectors are equal to each other, so equal to each other, we know they're parallel, they're also equal to, right? From here we can come out, this ABCD is a parallelogram. Okay, now let's look at the below one, the second one in the below. Okay, let's look at this one. Okay, so in this diagram, we will see three lines PQ, RS, and YX, right? Okay, so what are relationships? So the relationship is when RS equals to K times PQ, right? Okay, so RS equals to the K times PQ. Okay, so from here we know that. Okay, so then, and the K is more than 0, right? Okay, so we will know that. So we cannot. So RS is parallel to the PQ, right? These two lines is parallel. These two lines. In this case, actually, the magnitude is mu, and then RS is the half of this PQ's magnitudes. It's only half of them, right? So from here we know that, okay, so not only because of this, the length, the magnitude of this, also the Rs equals to K times PQ. That is magnitude, right? Okay, so we can see that because the K is more than greater than 0, right? So we also can say that, okay, they are all the same direction, okay, and the same direction. So we can see they are the same direction, right? Okay, so let's look at the next one. Okay, so the other one, the other one should be drawn this way. Okay, then we draw opposite direction to similar to this. So this one, okay, in this case, so when xy equals to the kpq, right? Xy equals to pq, and the k is less than 0, right? Is because this is minus 2/3, right? So it is the case because they are the opposite direction. Compared to this one, they are opposite direction. And also the key, this is the key, right? The key also less than 0. So we can see that, okay? So we can see that in fact they are the opposite direction, right? Opposite direction. So, and then we also can come up. Since these two vectors are equal to each other, we can see that x, y are parallel to each other. But just pay attention that and xy equal to the length, just in terms of magnitude is minus k times pq, right? So that is the relationship, right? Because they are the minus, right? Because k here is minus less than 0, so less than 0, so they are actually the opposite direction, right? So this is very good, right? Okay, this is the concept. Okay, let's go on to the example, right? Okay, let's move on to the example. Okay, now let's look at example 20. Okay, this is a solution here. Solution. Okay, so the first question is what? First question to show this AD equals to the BC, right? Okay, so this is the question, right? To show this. Okay, so because ABCD is a quadrilateral, right? Quadrilateral. So okay, so this, if this is the case, okay, and then also AB equals to DC, right? Okay, so now let's look at this one. So AD is what? Where's the AD? This is the AD, right? AD. So this is the AD, right? This is the AD. AD, so use the triangle law. So what's AD? AD belongs to what? AD is okay in the triangle of this. In the triangle of ACD, right? Okay, so what we get? Let's assume this is a triangle ACD. So what we get? AC plus CD, right? Use a triangle law. Here we're using triangle law, right? Okay, so what we get? Okay, so and then we also know, right? Okay, so because we're going to find the DC, right? DC, right? So we need to, okay, because we're going to find the B. Okay, so from here we see that AC equals to E, because we already know the DC. So from here we see plus CDC. Okay, just use the opposite because the negative, right? Just change. Okay, so in terms of vector DC, that is the other way, equals to the CD, right? So we can make it like this. Okay, and we also know that. Okay, we also know that. So AC DC equals to AD, right? AB, right? We just bring here. Just bring this here. Right? Okay, again, we're gonna change that. To B8, right? Okay, and then we just change the position. We can just change the position. So now here, so can we use the triangle law here? We just cancel off each other, right? What we get? BC, right? Can we get BC? Use the triangle law here. Again, we use the triangle law. Right? So we get an answer. The answer is what? AD equals to BC. Right? Right? So we can get an answer, right? Okay, so that's very straightforward, right? Okay, now let's look at the second question. So what type of this comparators of this ABCD? So basically, just look at this diagram. We will see this is the parallelogram, but we have to prove this. Okay, the key point of this question is we have to prove this comparator is a type of this comparator is actually a parallelogram. Okay, so that's the thing we're going to prove it. Okay, so this is the question A, right? Okay, now we already know this. Okay. Okay, second question. Okay, so second question. Okay, since we already know, because we already know, right? Okay, this AB equals to DC, right? AB equals to DC, right? So from here we know that, okay, so AB is parallel to DC, right? Okay, that's the first one. Okay, then we also know that, okay, in the question, in just now, this A, we already know AD equals to BC, right? So we also can come out, right? AD is parallel to BC, right? So that is very straightforward, right? So from here we know, because the both pairs of opposite sides are parallel, since the both pair of the opposite sides are parallel, right? What we get? We get A, B, C, D is a parallelogram, right? So this is the answer, right? So basically, so it's also, we have also find out. Okay, so this is for the question B, right? Okay, so from here we also can come out very important notes, right? Okay, this example is another proof that correlates is the parallelograms if one pair of its opposite side form an equal vector. Okay, so that proof is another proof that, okay, a comparator is a parallelogram with following two conditions. If one pair of its opposite sides form okay, so that's very clear, right? So if one pair of its opposite sides form an equal vector, then a comparator is a parallelogram. Okay, so that's a very important concept we get from this example. Okay, that's all for today's lesson. Thanks for watching. So in the next video, we'll continue to talk about the 5.4 applications of vectors in geometry. Thanks for watching. Bye.